There's some high school students coming to campus Friday for much of the day to just see there's various demonstrations being done. And I don't really know the extent of this. All I know is that Professor Loraz and I are giving a show starting at 9 in the slant room 117. And it takes roughly 45 minutes. So you're welcome to come. However, it's usually packed. So adults usually sit on the stairways, on either side of the slant room or in the back. Just to be aware of it. But it's acoustics and related, oscillations, related stuff. Okay, so we're going to finish this chapter today, the hydrophone chapter, chapter 8. We'll do a problem set tomorrow, and then I'll send out the quiz. And there's an experiment tomorrow, right? I guess it wasn't labeled as Lab 4 in the, okay. So we'll change that eventually. I got to remember to do that. But I think it was always in there. Okay. And this one's not too much work. In fact, the way we've done it lately, past years, a couple years, is Jay will explain everything to you, and then you'll just use his data. So it's not too bad.
It says Lab 4 on the Sakai. I've heard of that yesterday. Do you go down to week 9? It says Lab 4 in the.
No, the actual, I don't know, Gene. The actual document that I saw in the Dropbox didn't have a Lab 4 in the title of the, in the title of the document,
Yeah, it doesn't say anything.
So I think that's what caused the trouble. Is that right?
I'm looking for explicit, literal Lab 4. Just the titles, and it was reciprocity, something or another.
Yeah, it doesn't say the name.
So it wasn't in Sakai.
It's in Sakai.
It's in Sakai now. I
okay,
did
but yesterday it was not.
Yeah, when you gave me this, I knew exactly what I needed to do.
Okay.
So
all right.
It's there.
So of course it's all my fault. But so it wasn't in there. Okay, I'm sorry. I sort of was critical of you guys because I thought you weren't, you wanted to see Lab 4. I thought it was in there. When I got your message, I misinterpreted it. Okay, so it's in there now. Okay, good. All right. All right. So we're going to talk about noise in this lecture, and we're going to deal with a hydrophone system. Often people will just call this a hydrophone, but what they really mean is hydrophone system, and it includes the bare system, the thing that we've been talking about for months now, right? Plus a preamplifier. Always or almost always, you need some kind of amplification there. The signals tend to be so weak coming out of the bare hydrophone, typically like microvolts, that if you try to send it along some cable out, to get the information out, the noise is going to, the noise will be too strong. So this is what we're going to be talking about, a hydrophone system here. And noise, the definition of noise is very simple. It's the stuff you don't want. It's the part of the signal you're receiving. Well, it's part of the voltage, usually it's voltage that you're receiving, that you don't want there, you don't care about, okay? By definition, the signal is what you're interested in, and the noise is all the other stuff. Okay, it's that simple. So here's a diagram that I did that represents different types of noise. So this is the voltage of interest here, whatever it may be. And then, as I said, all this other stuff is noise, and it can be split in, first of all, into two basic categories. There's ambient acoustic noise from the environment, Okay, this is, well, okay, this is background sound in the medium. Okay, like if you're out in the ocean, there's noise from other sources. We'll talk about some of those sources in a minute. There's a number of them. Okay, that's all goes under the classification of ambient noise. And it can be split into natural noise and human-made noise. We'll talk about these in a moment. The other basic category here is noise from the hydrophone. It's unavoidable, as we'll see, that there's going to be noise. It's just unavoidable. How big it is, well, that's the whole point. How big is it compared to the signal? So the bottom line here is something you've all heard of. It's the signal-to-noise ratio. And incidentally, the signal-to-noise ratio is defined in terms of power. So it's the average power of the signal divided by the average power of the noise. Okay, so this ambient noise here splits into natural and human-made. Natural, just simply the fact that if we're thinking about the ocean here, but this is very general, the medium is at some temperature, the ocean or whatever, and due to the fact that it's at a temperature, there's random motion of the molecules in there, and that's going to generate pressure fluctuations, which causes sound. So it's unavoidable, just due to temperature, that you're going to have noise, and we'll see how that's quantified later. Guys, I'm going to split, this is too long of a paragraph here. I'm going to split that up, split this up. Right. Waves breaking. What happens when a wave breaks? You know, it's a pretty violent process, right? And it's going to generate sound. And incidentally, some of that sound, it's interesting. This wasn't nailed down until the 1980s. Some of that sound is due to the fact that when a wave crashes, but it was actually discovered for rain. A similar thing happens in rain when a raindrop comes down. What can happen is that it dents the surface of the water. And for a raindrop, what was discovered, and some of the fundamental experiments were actually done here at the Naval Postgraduate School in the physics department, okay, that a raindrop hits water, it indents it, there's sort of a conical indentation, and a wave is generated, a surface wave. That surface wave travels down to the vertex here and can pinch the energy intensifies, right? It's focusing. There's a focusing of energy, and it can pinch off a bubble, believe it or not. And there are great photographs of this happening. And you've created this bubble. So then, what do you think happens? Collapse. The bubble has transient motion, and it collapses, and it rings down. Noise. This is a primary cause of noise, and roughly the several kilohertz, roughly range around several kilohertz in the ocean. And kilohertz waves, can travel pretty good distance in the ocean. All right. We studied this last quarter, right? But anyway, yeah. So a lot of the noise in the ocean, at least in the roughly several kilohertz region, is due to rain, okay? And I'm guessing, actually, that this breaking of waves, that's one of the mechanisms by which that generates sound. And we've all seen this, right? We've all seen when a wave breaks. Well, I've seen it anyway in experiments, in acrylic, where I can see what's going on. You can see these bubbles being generated when a wave crashes. Seismic activity. Yep. This is, they've quantified noise in the ocean. Maybe some of you have seen this. So they have this spectrum here, and there'll be an amplitude, a measure of the noise spectrum as a function of frequency. And way down on the left, at really low frequency, it can be down, I think, even to millihertz, is seismic activity. Okay, that's what dominates at very low frequencies. And then they'll list the other things that dominate, and we'll be talking about some of those. Whales, other biological noise. Yeah, rain. And by the way, thunder. You know, now when there's thunder, I don't know how strong this is, okay? Because there's a big impedance mismatch between the air and the water. So most of the thunder noise is going to be reflected, but some will get in, of course. Right? Human-made noise. Okay, there's a ton of it out there nowadays. Shipping traffic, underwater communications and surveillance, underwater construction, and you know, other things, oil wells, you know, somebody banging on a pipe underneath. All right. Yeah, now on the other side here, the hydrophone noise, there's thermal noise because it's at some temperature. There's going to be thermal noise. We'll talk about that. There's other electronic noise, and also there's mechanical noise. The mechanical noise arises from the interaction of the hydrophone with the environment. And a good example is if you have this works for microphones in air too, right? But if you have a hydrophone here and there's a flow of water around it, right? There's a boundary layer here. If you know anything about fluid mechanics, there's a boundary layer. And the boundary layer can be turbulent, easily become turbulent. Turbulent means the fluid flow is randomly fluctuating. There's going to be pressure fluctuations. There's going to be sound. In air, that's called wind noise, right? And that's why sometimes you'll see reporters and stuff when they'll have a foam screen around a microphone. That's to cut down on the wind noise. Reporters, other people. Right, yeah, and hydrophones, you know, the coupling to the mounting platform. It's just endless here. Now, I want to make sure one understands this. What we normally call noise could be the signal. It's whatever you're interested in. It's up to us. It's whatever we're interested in. You know, this is an artificial, this is just for us here, this division. So for example, if you're interested in whales, the signal may be whale noise. What we would call whale noise, you would, I don't know if you'd call it noise, but even if you do, you really mean the signal, because that's what you're trying to detect. Now, there's two environments here. There's the one that I almost always stay in, and that's the laboratory environment, okay? Because things can get, I mentioned this a little bit before. Out in the field, so-called field, in this case for hydrophones it would be the ocean, or sometimes testing is done in lakes or large tanks, right? Extremely large tanks. Those are very different environments. And you find this out very quickly. For example, Stephen Faisal and I are thinking about measuring the Helmholtz resonance in a car as it's going down a road, okay? So you would be amazed at all the trouble just thinking about doing this experiment. In fact, there's so much trouble that now we're thinking, well, maybe we'll just pull it up to the loading dock and blast it with a large woofer and excite the Helmholtz resonance rather than doing it the way it naturally arises. So and if you've never experienced this, it's actually a good experience. But the experiments out in the field are just they just tend to be very difficult. Getting equipment out there, power, there's just a whole set of problems. And then another problem, of course, is that all the noise, right? It just tends to tend to be a lot of noise. We would be set up on the freeway or where we go to do this. If we do it, it's going to be there's going to be a lot of noise. So, so there are these two cases: a laboratory environment and a field environment. And often for acoustics, in a laboratory environment, you employ enclosures, pipes or chambers, like you've been in the anechoic chamber. You've done several experiments in there now. And we deal with enclosures for two reasons. One is to yield certain types of waves. Like we may have a standing wave tube, right? It's an enclosure, and we're interested in standing waves. Okay, you may want to anechoically terminate the end to deal with traveling waves. We've done that, and there was a research apparatus down in the hallway. It was removed 3 or so years ago during the renovation. But there is a traveling wave tube in the slant room. That white PVC thing running up the slant room there, I don't know if you guys have seen that. Yeah, that's a nonlinear acoustics tube. That's for demonstration purposes. We use it in the nonlinear course, which is not being offered next quarter for the first, well, but hopefully next year, okay? I don't know if I talked to you guys about that. Yeah, the nonlinear course, there's not enough students interested this year. So I guess I'm partially to blame for that. I guess I haven't been hyping it enough. But it's more complicated than that, but I'm not going to get into it. But hopefully next year and thereafter. So what that is there's some compression, some high intensity, higher frequency called compression drivers at the bottom end. And then at the top end, you don't see it, but there's foam rubber stuffed in the end there. And it's fairly anechoic. The pressure reflections are down by a factor of 100, the amplitude of the pressure. So another reason we use enclosures is noise, to shield the noise from the outside. People often don't talk about that. But it's all comes together. You know, you typically get louder, bigger amplitudes in an enclosure like that. You're also killing a lot of the noise that could otherwise be there. So out in the field and sometimes in the laboratory, there are standard methods to reduce noise. So we'll just talk in an ocean environment here. You can use a directional hydrophones. These are called vector sensors. Huge interest now and has been for at least 5 years. I've been hearing about people interested in vector sensors. So if you're trying to pick up some signal coming from some direction and you have noise, which tends to be isotropic, you can use a directional hydrophone, right? It's pretty obvious. You can also narrow the frequency range. It's pretty obvious. You can use an FFT analyzer. That's the easy thing to do. If you need to do better than that, you can use a lock-in amplifier. And I think I mentioned this to you guys, with the use of FFT, extensive use of FFT analyzers, fast Fourier transform analyzers, the lock-in lore, or what we used to call it lore, what am I searching for here? There's a lot of, it's kind of surprising, but a lot of science and technology is done just by, it's an oral tradition. You know, you would think in a technological society, everything would be documented and written down and just go, and it's just not the way it is. A lot of stuff is passed on orally and it's just never written down, okay? So what's happened, I think, with lock-ins is the people who've used lock-ins, and I've used them, they're, you know, they're not getting that much use in this. The usage of them has been in decline. But I can tell you, I know this for a fact, there's some cases where a lock-in will do better than an FFT analyzer. And we talked about this at the beginning of the, remember, first chapter or something, first week or so. So here, this is, yeah, I jumped ahead, but there are ways you can sort of stand fairly physically obvious things that you can do to reduce noise, due to mountings and stuff like that. Okay, now here's something that I've been wanting to do for, I think, 3 or maybe 4 years. So I put it in here to try to force me to do it, and I haven't done it. But now Faisal's going to do, Faisal and I are going to do this, part of his thesis. So the idea here, and I think we've talked about this before, but I can't remember. This is the simplest type of vector sensor, as far as I know. You can take two omnidirectional. This I'll be talking about. The demo here would be in air. Take two identical omnidirectional microphones, put them relatively close together, relative to the wavelength of sound, and you look at the difference voltage across there. So you actually take these two leads here, put it into a Stanford preamp, our favorite preamps, right? You guys have used these enough now, I think. And Stanford Research Systems. And those are only one channel. A lot of, when you first see them, they look like they're two channels. You see A and B, and you say, oh, and it's a really heavy. So you say, oh, this is going to be like audio land, you know, two channels. No, it's just one channel in there, okay? And, but the A and B, or if you want to do, one of the reasons is they have it is, so you can switch, toggle back and forth, but you can also look at the difference signal. So you just go to the, you just select the A minus B. It's called A minus B. It's not A dash B. That A, that's A minus B that you've probably seen in there. So it's relatively straightforward to do, and the idea is very simple. If a sound wave is coming from this direction, what are you going to read? Nothing, right? Ideally. And again, remember, we're thinking of long wavelengths here. If you want to quantify this, it's simplest in the long wavelength limit, and a lot simpler. You're going to get a maximum when it's coming this way, and it's because there's a phase difference between these two. You can pick up on that. And this can work. There are problems. The first thing you do if you build this, so we did this years ago in connection with some other research from Forefront Research. The first thing you would test this, we tested it in the anechoic chamber, we hit it with this and we saw a voltage. Okay, and you can probably guess why. You know, these microphones aren't identical. Even though these were, the sensitivities were close, within 1%. And I don't know if I told you guys this in the past, but that you can handle. You can use a potentiometer, you can hook up a potentiometer, you can make the sensitivities the same. But you know what killed it? Did I tell you guys about this before? The phase difference. Okay? When these are manufactured, at least the ones we were using, the piezo, the Endevco piezo resistive microphones, 1/8 inch, there was a phase difference there of like 3 or 4 degrees in the microphones. So when you hit it with a wave here, it's going to see the different. You're going to see a difference voltage. So that caused trouble for quantitative, for precise. We were looking for something for fairly precise quantitative measurements. For a demo, maybe we can just get away with this, right, Faisal? We'll see. But it is interesting, and you know, as I said, the Navy's very interested in vector sensors, and I don't even know if they've been. I assume that they've considered this, but I don't know. So for accuracy purposes, you might think, well, can we can adjust the sensitivities? Can we adjust the phase, you know, the phase coming out of here? Is there a phase adjuster? Well, that's a good question, and I don't know the answer yet. But Faisal and I might be considering that. I don't know. We have to wait and see. We'll see. This is going to give you the pressure gradient, the amplitude of the pressure gradient here. From Euler's equation, from the linearized Euler's equation, you can get the velocity. So you can think of this as a, you know, as a velocity transducer, but really what it should be called, at the heart of it, what you're measuring is technically is pressure gradient. So this is, in air, people will actually call this a pressure gradient microphone, and people have come up with other ones, other types. There's something called a ribbon microphone. Has anyone ever heard of a ribbon microphone? I have, and I have to be honest with you, I don't really understand. I'm going to look into it, just the basic operating principle, what it is. But what happens is with these microphones in the audio world is that, you know, like a singer will find, he or she will find that they can't live without this certain ribbon microphone. Ribbon microphones tend to boost, I think ribbon microphones tend to just naturally boost lower frequencies. Or I think it's a ribbon microphone. So the natural thing that you'd think of is, you know, these radio announcers always have these deep voices. Well, first of all, they were born, you know, they were all born that way. You know, when they were, I think a lot of this is natural. And then they're trained, right? But there's this other thing that I've always wondered about is they have their special microphones too, I think, okay? And maybe they're using microphones that tend to enhance the bass, right? That's one of the ways they can do that. So, you know, maybe we can all be radio announcers if you want to be, I don't know. Yeah, okay. Okay, so first we're going to talk about thermal noise. So the fact that you've got a substance, whatever it is, isn't solid, liquid, gas, because it's not going to be at absolute zero, right? There's thermal motion, there's going to be fluctuations, and there's going to be sound. So here's how that's, I'm just going to briefly talk to you about how that's calculated. This is a pretty standard calculation that interestingly enough is in nearly all modern physics books. Okay, why is it in modern physics books? Some of you have taken modern physics, the combat systems students, right? The USW students, I'll bet you don't. Well, who are the USW students besides Faisal?
But I did because I'm in applied physics as well.
Oh, okay. Sean, are you USW? I've forgotten, sorry.
Yeah.
So, Stilson? Yeah, you know, it's really good to take modern physics. It's actually fun. And the emphasis is on concepts rather than calculating things, although you do some calculations. Mark, you took it from me, right? Okay, that's why you're smiling. Okay, so yeah, it has this tradition. It's sort of a impedance match from classical physics to quantum mechanics. And it was discovered like a century ago. There's a long history of the education here. I'm getting way off on tangent here, but it's really interesting, especially in modern, our modern technology world. Almost all devices involve quantum mechanics now. So you can learn about this just from a basic modern physics course. And I'll mention later in a few minutes why this calculation is in there. But here's the idea. Consider you've got some medium, whatever it is. And suppose you have, it's in a box. It has a boundary. And we're going to make this big. We actually let it go to infinity later. And you have some kind of boundary conditions. It doesn't matter what they are. And you look at all possible, we're interested in acoustics here, so we're going to look at all possible standing waves that can exist in there. We know that any acoustic noise or any acoustic disturbance in there can be represented as a superposition over all these nice standing wave modes. That's the whole idea of normal mode analysis. I don't know if, and you can, to appreciate it, just think Fourier analysis. You know, just from the basic math of Fourier analysis, you can represent any excitation of a system by a superposition of these nice, in this case, nice standing waves, right? So then we use because thermal motion is random, energy is moving around, it's randomized. We use this famous equal partition theory of classical statistical mechanics. And it says simply that there's an average energy of 1/2 k Boltzmann T for each degree of freedom. So this is for random systems. Energy likes to be, on the average, equal partition among all the possible places where the energy can reside. Furthermore, quantitatively, there's an average energy of 1/2 kBT. This is Boltzmann's constant. This is the absolute temperature. Okay? So it's actually, equal partition is reasonable. And it's reasonable that it should be, proportional to the temperature. Now, we actually have 2 degrees of freedom for each standing wave because there's kinetic and potential energy in a standing wave. So there's a factor of 2 in there. So when you, the result of this, once you have all these modes, is you can show, in modern physics books, it's done from the viewpoint of electromagnetic waves. Here we're dealing with acoustic waves, but it's very, very similar, same idea. You can show that this quantity, and what does this mean? This is the time average of the square pressure here. The T stands for thermal. We're talking about thermal noise here. But there's something else going on here. You want to think of this, the fact that this is subscripted. This is P squared is proportional to the energy density, the energy per unit volume, as we saw last quarter, right? Square root of the pressure. This is also a spectral quantity. It's per unit frequency. So this is not, this P here sub T is squared is per unit frequency. So this is what you find, so this is proportional to the spectral energy density, the spectral energy per unit volume, okay, which is measured in per hertz. And it's got a kBT here because there's, that's there because there's an average energy of 1/2 kBT for each mode. And you'll notice this F squared here. It increases with the frequency. Why do you think that is? Well, there's a lot more modes at higher frequency, obviously. That's why that's there. So this is famous. It means that when you integrate over this, over all frequency to find the total energy, it's infinite, which is obviously not right. And that was resolved in 1903 or something like that, you know, the late 1800s, early 1900s, by quantum mechanics. It was Planck who argued, actually, it wasn't really physical, it was just a mathematical argument, but he turned out to be right. Okay, it was Einstein who pointed out the physics behind it. That when you get to very high frequencies here, the classical physics breaks down. You got to look at it quantum mechanically, and the energy is quantized in a photon. You've all heard of photon. In acoustics, I don't know if you've heard this, but the same thing happens. It's very general. Energy is discretized. Those are called phonons. How many people have heard of that? Not just a few. Yeah. So everyone's heard of a photon, right? So, you know, that probably happened with Star Trek, the television series. Right? And why is that in the news? Anyone? Yeah. Spock. Yeah, we don't call him literally, we just call him Spock. Yeah, he died recently, okay? There's tons of stuff in New York Times on this. Maybe I should put the obituary on my front door. Anyway, the same thing happens here. So you avoid this infinity. At the very high frequencies, you've got to recognize that the energy is quantized, and that Planck's hypothesis was that energy, that quantum of energy, is proportional to the frequency. So you just can't dump arbitrarily large amounts of energy in these short wavelength things, because the quantum becomes quite large because the quantum of energy is proportional to the frequency. So that avoids this divergence here in the total energy. So now I want to point something out to you here. This is per unit. This is proportional to the energy density, energy per unit volume, per unit frequency. I'm going to say this now, even though it's not. It'll be in the notes later, but it's important for you to recognize this. We want to deal with pressure. In acoustics, we almost always deal with pressure rather than intensity or energy. So we take the square root of this. So what happens to the per hertz? The energy density per hertz. Energy per unit volume per hertz. When we take the square root, we get something proportional to pressure. What happens to the frequency interval? It becomes square root hertz. So you'll see this everywhere. In noise specifications, you'll see, you know, Pascal or something per square root hertz. And that's why the square root is there. It looks strange when you first see it. So if I wanted to find the average pressure in a band of frequencies, a relatively small band of frequencies, I would take this number and multiply. I would take this number, take the square root, right? Because this is squared, so we're getting an RMS type value of the pressure. And this is something we can appreciate and compare to our signal, the amplitude of our signal. That's why people deal with this. But then what do I have to do? I have this. This is a broadband spectrum. I have to multiply by the interval, okay? And there you have to multiply this by the square root of the interval in hertz. That's why so this is kind of, when you first encounter this, I remember when I was an undergrad seeing it and saying, why is there a square root there? Why would they do that? Well, it's because it's energy based. It's energy per unit hertz is the natural way to do it. But we want to deal with amplitude, so we take the square root, and that's how the square root hurts. It's that simple. But I think it throws people in the beginning. Okay, I've already talked about this. This is quantum mechanics. And here we go. So you'll see this in Pascal per square root hertz. We just talked about that. So for the ocean, people naturally use a decibel measure, a level. So here's how it's defined. We take the square root of that equation, because we're going to deal with, this is amplitude based rather than energy based. We want to deal with it on an amplitude level. So you take the first thing is you take the square root, and then the reference value here is chosen to be 1 micropascal per square root hertz. If you're going to have a dB measure, you've got to have a reference level. right? Unless you're talking about a change in decibels. Then it cancels out if you remember that. But in general, to accurately define this absolute dB or measure or level decibel measure, you need a reference. So this is what's chosen. Then you take the logarithm to the base 10 and then you multiply by what? 10 or 20. Why 20? Because it's amplitude based, right? And here's what you get. Okay? So this is the F is here because this is a spectral quantity. You know, it's per frequency range. And as an example here, if you want to apply this, F is in, oh, so this, it's understood here, F is in hertz, okay? And we put the, here's the reference level, because otherwise you wouldn't know what the absolute intensity or what the RMS pressure is. You need to know the reference level. There it is. So as an example here, if you're, suppose you're in a region of 100 kilohertz. Okay, so remember, this is due to thermal noise. This is due to thermal noise right here. We're talking about the thermal noise. Oh, thermal noise is, yeah, it's called thermal noise. Never mind. Okay, so we take 100 kilohertz. What's the bandwidth? Well, often people take a 1 hertz bandwidth. So the square root ends up not really being important. But if you have a bigger bandwidth, if you have 10 hertz, you're going to have to take the square root of 10, which is approximately pi, and make sure you multiply by that to get the total RMS pressure level in that 1 hertz band. It's equivalent to a sound wave of 25 dBs, 25 dB. Now it turns out that this this thermal noise here in the ocean dominates roughly 50 kilohertz and above. All right, and below that you start to hit all these other sources. And again, it's actually, you can see spectrums of this where it's labeled what's dominating in the different regions, as I discussed before. So this has been empirically quantified. Some of you may be familiar with this if you're a submariner or something like that. Did you guys ever deal with this? I mean, somebody's going to need to know about this, you know, I would think. No comments? Okay. Okay, so now, yeah.
We use always 1 hertz band.
Typically people use 1 hertz when they want to get a feeling, you know, because you're ending up, you got a pressure here per square root hertz. The units are telling you that you don't have pascals, okay, and you want to compare it to a signal that has so many pascals. So you got to have a bandwidth there. This is broadband, it's continuous. Typically people will multiply by 1 hertz, which then you don't have to worry about the square root, as I mentioned. But it all depends on what you're after. You just need to know why it's there. This is an energy density in 2 respects. There's an acoustic energy per unit volume, and there's an acoustic, and then that is per unit frequency. It's spread out in frequency. It's broadband. So to get the energy, you're going to have to multiply, not just by a volume, which is pretty obvious. If you really want an energy, you have to consider the volume. Take the energy density and multiply by some volume. You also need to multiply by a frequency range. It's a density. It's a density in 2 respects. Okay, now we're not going to go through the mathematical analysis here. I did that once the first time I taught this course, and then I realized I would never do it again. You really don't learn anything from going through the math. We're just going to state the results. But we want to set things up. It's important with some more ideas we need to get in here. All right? So I'm actually going to, just so you'll know when you get the revised notes, this long calculation, complicated calculation here, which is from the book. I'm going to separate that out into a final section and call that optional. I should have done this years ago. And the essential stuff that we need to see, that'll be in this section right here, and then I'll remove that. That'll be on just for the mathematical analysis. So we're just going to go, we're going to talk a little bit about this and then jump to the results. Okay, so here's how we're going to sort of set things up. Here's how the analysis can proceed here. We need to include a preamplifier because, again, it's almost always necessary to have that, as I mentioned before, because typically you'll be swamped with noise that comes in on the transmission of the signal if you don't preamp it close to the source, close to the hydrophone, okay? We have to recognize that any amplifier, it's going to produce noise. For example, it's at some temperature, so there's going to be that kind of noise. And there's other types of noise. We're not going to get into that here. But if you open up any electronics book, in fact, I had to do it this morning because I was having some trouble with some of this, you'll find descriptions of different types of noise. Right? Some of you have probably experienced this in electronics course, maybe here. Right. So here's the model. Now this is reading the, usually for a hydrophone, we think of this has been flipped for us. But here's the signals being measured by the hydrophone. And this is the hydrophone amplifier system. This is all one system. Okay, but we split it up here in order to delineate or see the different effects. Here's what we're well accustomed to for piezoelectric hydrophone. And then this is the mechanical side. Here's the electrical side. You can see there's a blockage resistance there. Okay, and now this represents an ideal amplifier with no noise, and you can put in a voltage and current sources here to model that. Now, in the analysis, approximations are made. We don't need to really worry about this right now. Okay, and we don't need to worry about it here and what I'm going to say here. But I do want to mention the fact that, again, we have to deal with the noise from the preamplifier. And there is, one source of noise is anytime you have any kind of resistor, you're going to have noise. Because it's a thermal thing. The fact that the resistor is at some temperature. And it turns out, and I need to improve this, okay, that's why I opened up a book this morning. It's the conduction electrons in the resistor. Because it's some temperature, those electrons are going to be randomly moving around. And so the voltage can fluctuate because of that. And this is a famous thing. It's also called Nyquist noise, which many of you have probably heard. Named after the person who, I guess, first quantified this or something. I don't know the history. So here's what it is. If you have any electrical resistance at some absolute temperature T, this is the average square of the voltage. And there's a mistake here, and I think you can infer that this is lowercase. But let me just tell you, this is per unit frequency. Okay, so I'll be editing that. This expression here this is a broadband, a continuous spectrum. This is per hertz. Okay, it's per unit frequency. So this is a spectrum. So as an example, if you want to, if you have I'm going to change this. For one thing, this is incorrect here. Here's the resistance. Here's the temperature. And I take the square root to get the RMS voltage. What's the band? What's the frequency band? What's the frequency interval? So this is absolutely wrong. Okay, I screwed up here. We need to multiply by a band. Typical bands are in a measurement device could be, 10. The one that in the book I found it shows 10 kilohertz. So I'm going to do that. I'm going to modify this. But this is wrong. This is per unit hertz here. And of course, when you take the square root to convert the square voltage into voltage, you have per square root hertz, just like in the pressure. Now you might say, well, this is small, it's microvolts, but as we've seen, that's what you can get out of the bare hydrophone is typically microvolts, right? So they can be comparable. And incidentally, this is why in some, in unusual cases, I can't think of any examples right now. People will cool electronics with liquid nitrogen. And why are they doing that? There's Nyquist, the thermal noise here, to reduce it. Anybody know of an example? I knew of one. It was something actually on a satellite. There was some astronomical or cosmological thing. Yeah, I don't know any examples. I can't remember any, but this has happened. People go to the trouble to use liquid nitrogen, and it's ordered to. Apparently the Nyquist noise is dominating, and they want to beat it down because they're looking for a very weak signal. Oh, so at this point, we're going to go to the result, okay? And again, I'm going to extract this calculation out and put it in a final section that's going to be optional. And you know what optional means. In this case, forget it. I just can't, I put all this effort into going through this. My first time I was preparing for this course, and I just can't delete it, So, you can see, it's just it looks like a nightmare here. Oh, here's the signal to noise ratio. People usually call it S/N. I think that also can stand for serial number. Is that right? Oh boy, okay, so. Okay, so here we're going to jump to the end here. Let me make sure I'm doing this right. Yeah, okay. So we're going to jump to the end here. So we really need to start here. So the figure of merit, how good your hydrophone system is. And this is going to be obvious when I tell it to you, but you probably won't be thinking it right now. You've got this hydrophone, you're in some environment where you have all this ambient noise. You really can't do much about the ambient noise, all right? And the ocean is especially tough. Here in the lab, if we have a problem with noise, okay, we come in late at night, okay, when the building's more quiet or something like that, right? I don't think it's going to work in the ocean. It's like 24 hours, it's on 24/7, right? So anyway, what you want here is you want to reduce, you're going to have to deal with the ambient noise. You really can't do anything. You want to reduce the noise of your hydrophone system compared to the ambient noise. So the natural thing to compare it to is the ambient noise. That's the sort of figure of merit here. So that's what I think is stated here. The hydrophone spectral noise pressure. This is coming from the hydrophone system, including a preamp, right? You want it to be small. You want to look at the ratio of that compared to the spectral noise pressure from the ambient, from the ocean, okay? The smaller it is, the smaller that ratio is, the better off you are. So this M, incidentally, is not mass, it's open circuit sensitivity. I got this from the book. I'm going to put a 0 in here to try to avoid a little bit of confusion. So here's the conclusion of, here's the conclusion. I don't think either of these is obvious. Well, and the second one's quantitative. I don't think they're physically obvious. Maybe, somebody who's an expert in this has a physical feel for it, but I don't have it. So there's two things that we conclude here. This noise performance here, this figure of merit, to beat down the noise of the hydrophone system, is improved if the volume of the piezoelectric material is increased. Now that kind of sounds reasonable. You might think, the bigger this is, the more mass you have, the less noise you're going to be subject. It kind of makes sense, but I want to point something out. It just sort of feels right. It's not volume, it's not mass, it's not density, it's volume. If it were mass, the total mass, there would be a total mass of the ceramic in there. So I don't know physically what's going on here, but anyway, this is one of the conclusions from the calculation here. The other one is, and we talked a little bit about this before, is you see this quantity, this is something we have control over here. Oh, GH, it's the total effective G. So for the rectangular block, GH is 2, I think it was, remember this? So when we have a rectangular block exposed to pressure on all sides, the relevant quantity here for the transduction, you know, the relevance, like the little d, same, it's similar to this. This is what's the relevant quantity. So this is, we're just lump, all it's, these individual things aren't relevant, it's just the total. So we lump that all into this GH here. So we have control. We can choose different materials, right? For this quantity right here. So if you look at this, you want to maximize the dielectric constant times the G. Okay? Now we can introduce D here. We can get rid of epsilon and introduce D. So this then is just the product of DG. So the product of DG is kind of seems like it's a sort of a famous thing. It's tabulated because this, you want to maximize this to minimize hydrophone noise. So it's so important that you can actually find it. You don't have to hunt for D and G and then punch it, take the product on your calculator. They've already done it for you. So that tells you right there this must be important, right? And that's what emerges from the theory here. Okay, anybody have any questions or comments? Okay, so problems tomorrow. I want to warn you that everything's going to be due by the end of next week.